So here are satellite observations of something that is called ocean color, which is a proxy of the surface chlorophyll A concentration. Chlorophyll A is the green pigment in phytoplankton. Okay. All right, here are the distributions, summer and winter distributions. Okay. On the left side, the Peru-Chile upwelling system, also known as the Humboldt current upwelling system. And on the right-hand side, the California current upwelling. What you can see there is the range of chlorophyll A values, where the maximum is in red. It's 10 milligrams per cubic meter. So that's a typical range of typical maximum that you get for these coastal upwelling. And you can see that they spread over long distances. Yeah, you can see that the equator is indicated here in the top, indicated here in this figure, and you can see the stretches over. This is about 1,000 kilometers. Okay, so these are massive. There's some seasonal variability in the upwelling intensity, as you can see here. Just the difference between summer and winter. Okay, because the winds change their change. Okay, also the latitudinal extent varies between the season. Anyway, okay, so you can here the California current upwelling system. You can identify it near the coast through elevated chlorophyll A concentrations. Yeah. What you often also can see in these images is the creation of oceanic eddies. Okay? Eddies are circular patterns, and these eddies, they move water that's high in chlorophyll away from the coast in something that we call filaments, little streaks of chlorophyll rich water. Okay? Probably if you look at that, you can also see that there are some regions which stand out more, which have higher values. And we call these regions upwelling centers. All right, so some underwater observations from the Peru-Chile upwelling system. Okay, so here are some measurements actually taken from a boat, okay, with so-called CTD instruments. Okay? And here are some reconstructed maps. It's not only CTD, but also current meters that determine the horizontal flow component. Now, for example, here, let's have a look at the panel D. Panel D is a top view. It's the surface distribution, essentially, of temperature, but not from a satellite, but determined from the vessel. So upwelling you can easily identify by the regions where you have the coldest water. Okay, because the only mechanism that can actually induce cold water near the surface is the upwelling, the vertical upward movement of colder water to the surface. Okay, here you can see the observations, and what's shown here are these little dots are actually the regions where the observations were taken. So these are the field stations. Okay, and based on the observations or the values at the field stations, they created this contours. Here's a 19 degrees Celsius contour, 18 degrees Celsius, 20 degrees. You can identify here there are 3 regions which have a locally the coldest surface water, and these are upwelling centers. Okay, so individual regions where you anticipate where the nutrient concentrations are highest of the water that's brought into the footing. And let's have a look at panel C. This is now a vertical transect, okay, where you are cutting across the shelf break and then end up at from right to left. And you can see the upwelling in this field. See the upwelling here. You can see that this orange layer, orange water, okay, which is below 16 degrees, it's actually moved to the surface as you go closer. Okay. The colors are a little bit misleading in this graph. You can see that this orange here in panel C corresponds to the blue in panel D. Anyway, what do you get from that? You actually can estimate the depth where the water comes from. And it's not very deep, this upwelling. It comes from around 100 meters. Okay, you can see upwelling. Below 100 meters, you can actually see some downwelling. Okay, so it's relatively shallow, the upwelling. In panel B, you get some estimates of the cross-shore velocity field. And here you can see an offshore Ekman layer near the surface. And you can see an onshore movement at depth. Okay? And the longshore velocity in panel A gives you an indication of, it's not very strong here, it's only 10 centimeters per second, but it gives you an indication of a longshore geostrophic jet. Okay, so you learn quite a bit from just looking at these structures in terms of the temperature field and the velocity field.